Welcome to the Reinforcement Learning Reading Group of Edinburgh. Today we have a guest from the University of Milano, Riccardo, who is going to present a couple of papers, if I understand correctly, on exploration in partially observable MDPs. So Riccardo is a PhD student under the supervision of M. Restelli at Politecnico di Milano. His research focuses on developing principled algorithms to pass over current limitations in multi-agent RL. So Riccardo, we're super glad to have you today, and I'm looking forward to your presentation.
Thank you. Thank you so much. Thank you for having me here, and I hope all you can see the screen. So the topic of my talk will be mostly about pure exploration in POMDPs. I will present its intrinsic limits and some possible solutions. And these topics were covered mostly in two recent papers recently published. I will talk mostly about the first one, called The Limits of Pure Exploration in POMDPs, and I will briefly sketch some topics from the second one, which goes beyond observations, and is called How to Explore with Belief. That works were done together with my colleagues, Duilio Cirino, Marcello Restelli, and Mirko Mutti. So just to give you an outline of the topics I will touch, I will provide just a brief motivation under our research questions. I will then describe the problem setting and the right formulation to address the problem setting. I will provide some objectives which can be used to address the problem we are interested in too, so pure exploration in POMDPs. And I will provide some theoretical guarantees describing the gaps between the possible objectives that we might want to tackle. I will then touch some possible algorithmic solutions to the problem with some empirical validation on some toy examples. And then I will provide a further extension, a regularized algorithm that is able to circumvent the intrinsic limitations of POMDPs, at least partially. Then I will again try to go beyond observations, addressing the problem of pure exploration in POMDPs, dealing with models over the latent space. And I will describe the problem settings, the objectives, and briefly some results. If we have time, we will touch the proofs, which I really like, but it won't be the case, I guess. So first of all, why are we interested into this problem? Let's imagine a rover that has to visit a recently found planet, let's say, and it's supposed to explore its surface. Usually in RL agents, most of the tasks assume to have access to a pretty nice representation of the space, often coherent with the task. And here we are talking about the task of exploring the environment. Most of the time, this task is rather interesting by itself, and you want to have almost a uniform chance to be everywhere while exploring. Often enough, you start by exploring the environment, and then you might find out that you want to perform other tasks as well. Again, this is pretty known how to be done in MDPs, having access to the state space. But in most of the cases, and in real cases, we don't have access to the state space or a representation of it. We rather have access to partial observations about it, like cameras providing information about where their surroundings of the agents only. So this setting about pure exploration, so exploring in a uniform way the state space, usually goes under the setting of POMDPs when we have just partial observations. And POMDPs are rather easy to model. We have, as always, an agent, environment. The agent finds itself in a state S. Unfortunately, it acquires just partial observations about the environment X coming from some observation matrix, which is a conditional distribution over the set X. And based on these observations, It usually performs actions sampling from distributions called policies, which are conditioned on a generic set I. And these actions lead to the evolution of the system to a new state as t+1. The interaction starts with an initial state sampled from a distribution mu and goes on up to an horizon capital T. And usually the information set the agent uses in POMDPs is either the observation directly, leading to Markovian policy over observations, or more frequently, non-Markovian policies over trajectories of observations. And we'll denote these trajectories with bold letters. So having to deal with pure exploration and having to perform downstream tasks later on is usually modeled through the formulation of unsupervised RL, which is usually built of two different phases, at least as it was at first introduced. A first phase of unsupervised pre-training, when we have, in case of MDPs, for example, a controlled Markov process without any kind of reward. And the task is to pre-train a model that will be later on used on a supervised fine-tuning phase, a second phase, of which consists of the standard RL phase, let's say, like finding the optimal policy. And this phase starts as soon as the controlled Markov process is equipped with a reward, or this reward might change with time and the agent might be called to perform different tasks. So you might wonder, what is this model actually? This model is found trying to maximizing some unsupervised pre-training objective, which is totally agnostic of the rewards the agent might face later. And usually these models actually depends on the literature, but usually the class of models might be the transition models, which will be later on used in model-based RL, for example, some state representations in order to build good representations of the states, some policy spaces in order to learn like reduced size policy spaces so that the search over the policies will be faster, datasets, if you are interested into offline RL, for example, or policies. And we are interested into this one in particular. So as long as you're looking for a policy in the unsupervised pre-training objective, another common function to be used is the entropy of the visitation distribution induced by the policy over the states. So if you take the probability to be in any possible state over the horizon T, conditioned by following a specific policy pi, you will be looking for the policy which induces a distribution as much entropic as possible, so almost uniform possibly. This objective is rather interesting. It was proved to be way harder than standard RL, since it goes under the framework of convex RL. And it provides a policy which is able to, at least in MDPs, to visit any possible state with kind of the same probability in any possible time step. And this could be a policy to be used later on to jumpstart the learning in subsequent phases, as it was used in the Jumpstart Reinforcement Learning paper by 2022. Trying to maximize these objectives corresponds to the so-called maximum state entropy objective, which was defined by Hassan in 2019 for MDPs. But we are dealing with POMDPs actually. And yes, Samuel, I think you have a question?
Yeah, I just wanted if you could you maybe give an intuition as to why the maximum state entropy RL problem is more difficult than the standard RL problem, and maybe like
I see.
Also like a easy definition of like what's convex RL.
Yes.
I'm super familiar with the.
Yes. Oh, sorry. So in general, convex RL. If you have an MDP, you usually are able to define an MDP, the objective of optimizing over MDPs to find the optimal policy, like an expectation over the discounted distribution or the average distribution, which is the expectation of the rewards with respect to this distribution. So it's actually linear over the rewards. The rewards might be a complex function, but then it's a linear product between the distribution and the rewards in general. Convex RL deals with any kind of scenario in which the function is actually non-linear, and this leads to some kind of hard results in the sense that it really depends on the function and so on. There are easy problems in convex RL in which you can, task convex RL as a simple standard reinforcement learning task, but most of the cases this is not possible, and it was noticed that specific tools need to be devised to solve it. So in a sense, it generalizes standard reinforcement learning to more complex objectives, which are not just trying to optimize the expectation of the reward.
Right, and then because the entropy of the state is a nonlinear function, then that becomes like a convex RL.
Yes.
In this case.
Yeah.
Okay,
then
awesome.
specifically here, it's a concave, but yeah, I mean, it's just about the terminology. The terminology would be the same. Yes.
Okay. Thanks for clarifying.
Oh, no worries. Anyway, I reported some references if you're curious about it, and you will have the chance to see it at the end. So we are interested into maximum state entropy, which is well defined at least for MDPs. But what if we have POMDPs? So in POMDPs, we don't have access to the states. So if the agent navigates through the environment, seeing some states and extracting some distribution over the states, actually in maximum state entropy, it will try to reach as much uniform distribution as possible, but this quantity is not available in POMDPs, while on the other hand, the downstream tasks might be defined over the state space actually, like the rewards in POMDPs are often defined over the state space. And that's why our main objective will be still to maximize the state entropy, while not having access to states. What can we do? The most straightforward option would be to extract distribution over observations, which might be extremely different from the distribution over the states, and optimize for the entropy of the observation distribution. So you interact with the environment, you extract the distribution of the observations, and you try to maximize this quantity. As you can imagine, this mismatch between the quantities we're dealing with might lead to a rather non-negligible mismatch between the performances. And that's what we first addressed in our paper. So we defined the maximum observation entropy objective, and we studied the gap between these two quantities. So imagine that you want to control the maximum observation entropy, for example, because that's the only quantity you can have information about. But your real deal is about the state entropy. So the first gap we derived was a spectral approximation gap with this bidirectional bound. As you can see here, the state entropy and the observation entropy are linked through the maximum singular value of the observation matrix. Either the maximum singular value of the observation matrix or the maximum singular value of its Hadamard inverse, which is just the same matrix with, in any element, the inverse of the respective element. So you can see here, just to provide some visual intuition, that there are many scenarios that can be easily described by this gap. Let's imagine, for example, that you have a totally destroyed camera, which provides you with blacked out information, like just black screen. This means that no matter what the state, here I represented the observation matrix, no matter what the state is, you will always have almost with probability almost 1, always a black screen. Actually, this is the worst case in terms of maximum singular value, and the bound prescribes a pretty bad scenario. So the two quantities might be extremely far away from each other. So you might think to be really good, and you might be really bad. Or you might think to be really bad because you're going in black mode, but you are actually pretty good. You don't have any information about it. On the other hand, in the scenario in which for any specific state, the observations are such that you almost get one specific observation for any specific state, like the one over here, then in this case, the gap is really little. And it's a pretty good setting to perform these kind of tasks. So to sum up, it's a pretty nice bound. It's bidirectional. It's elegant. But on the other hand, it has pretty strange dependency on the observation matrix. It's pretty hard to know how the bound will behave in any in-between setting. And most of all, it's independent on the policy. So no matter what the behavior of the agent will be, this gap is about the spectral properties of the POMDP, and the agent has little to do about it. So we derived a second bound, an information approximation bound, which is just a lower bound. But we're fine with it because we will try to optimize this function over here, which lower bounds the real objective. So at least we will have non-degradation. And they are linked through the expected value of the entropy of the observation function. So just to give another intuition, imagine to have a policy which visits states with high probability, over which the observations are almost uniform, which means highly entropic. Here comes the conditioning over the state as visited by the policy. This case is rather bad, and the gap is rather loose. So in this setting, you don't have any good guarantee that having high entropy over observations might lead to high entropy over states. On the other hand, if you visit with your policy states which provide you almost extremely precise observations, like this case, for example, you have good guarantees to be performing well over the latent states, even if you don't see them at all. So there are pros, like the fact that there is some implicit dependency, at least on the policy, since both the conditioning and the expectation is based through the policy, but it's a lower bound only, but more importantly, is inaccessible in POMDPs in general, since it's based over the states and the conditioning is over the states. So we wondered, can we do better? Fortunately, yes. By slightly playing around, we were able to derive the second bound, where we shifted the conditioning and the expectation, so that the expectation is taken with respect to the states that the agent actually sees during exploration, and the conditioning is taken with respect to the observations as well. So it's about the entropy of the inverse observation function. Here again, while here this was the previous case, right now we're caring about the observations that the policy induces, and we care about visiting observations which might be generated by just some specific state or just a specific subset, like in this case. On the other hand, if we visit observations which might be generated by any kind of possible state, like for example a black screen again, this is a bad scenario as well. So this is a pretty good bound again. It's conditioned over observations only, and it's dependent on the policy. So it's pretty actionable by the agent. We focused on how to optimize this quantity as well. And before going on, I don't know if any of you have some questions, feel free to ask. Otherwise, I will just go on with the... Yes?
Maybe just a quick one. I was wondering if like you had, and you may have said it already, and I didn't pay attention, but do you have some assumptions you make on the POMDP structure, on the relationship between a state and an observation, like for example, like a block MDP assumption?
No, there is no assumption over the structure of the observation, out of the fact that we are dealing with discrete sets, just to make the analysis easier. Consider that the pure exploration problem would be extremely hard in continuous MDPs as well. So as a first step, we took into account discrete sets for POMDPs, but this is the only assumption. These are just about the properties of the POMDP by itself. Then it might be that the bounds are behaving better or worse depending on how the POMDP is structured. But in general, these bounds remain valid if you deal with discrete sets.
Okay, awesome, thanks.
So we focus on how to optimize for this quantity. As I said before, this is a rather hard quantity to optimize for. And as a first step, we derived a fairly relaxation to optimizing for this quantity. So we passed through trajectories. So imagine to have, instead of extracting the exact distribution of the observations, you sample trajectories of observations from the distribution Q while interacting with the environment, and you compute the empirical distribution of the observations conditioned on the trajectory you have seen. By introducing this conditional entropy, which is just the entropy of the conditional distribution over observations, we define the trajectory-based formulation of the previous objective, which just consists of taking the expectation with respect to trajectories and then computing the conditional entropy. Fortunately, this is a lower bound due to Jensen, so optimizing for this quantity at least does guarantee a non-degradation in the original objective. But most importantly, this objective is a standard RL objective, which can be addressed with simple algorithms like the one here with a policy gradient approach. So in a policy gradient approach, we call the MOE policy gradient. We sample trajectories, we compute feedbacks according to the function we are trying to optimize for. We compute score functions as well, and we perform gradient steps towards the direction of best improvement. We tested this simple algorithm in some toy examples. For example, you see here a grid word with some Gaussian observation matrix, meaning that the mean of the Gaussian is the actual state of the agent, but there is some variance over this Gaussian, and the agent might be scattered towards a different state with respect to the one it is actually in. So we wondered what happens once we play with the quality of the observations. Does it impact the performance of the algorithm as we would expect from the theoretical study? So we use different noise level in the observations so that we were able to define well-behaved and bad-behaved observation matrices according to the bounds we described before. And we plotted the true state entropy over the y-axis. So you need this is the quantity you see over here is the actual entropy over the states the agent is able to achieve, even if it doesn't have access to. The green line corresponds to using as a feedback the true state entropy as well. This is not possible in POMDPs in general, but here we wanted to test the algorithm against the best scenario, like using the true actual feedback. On the other hand, we tested in the yellow line using the observation entropy as well. As you can see here, when the observations are well behaved, the gap between using these two feedbacks is pretty negligible. On the other hand, when the observations are really noisy, or even in between cases like this one, the performance undergoes a pretty fair degradation. And we wondered, is it possible to reach some in-between case? Like even if the observations are really bad in general, in the sense of the bounds, we're still able to recover slightly with respect to the best case of using the states as well. So in order to do it, we followed the lead of the information approximation bound, and we derived a regularized objective. It is still an trajectory-based formulation, but here, as you can see here, we added a term equivalent to the term in the information approximation bound. This term takes explicitly into account the uncertainty of the POMDP and the uncertainty that dealing with observations lead to in terms of performance, because it's the expected value with respect to the empirical distribution of the entropy of the observations. So if we suppose to have access to this information, which might not be the case, but in case we have access to this information, we can actually look for observations which lead to low entropic feedbacks. And we rather are looking for observations where the entropy, where the distribution over the states is like this rather than this. So that we can still perform policy gradient methods is still a valid objective to perform gradients over by just adding some regularization step. And this was exactly the red line we plotted in general. And as you can see here, we are able to recover slightly the performances, even if in this case, the noise was almost like the observations were almost random. So the agent was scattered almost everywhere in the latent states. And where this was because the agent was actually able to exploit the structure of the POMDP. And with structure, we mean that in this specific environment, we added a so-called glass state or visible state in which once reached this goal state, the agent was able to improve the observation matrix towards an almost deterministic observation matrix. So this performance corresponds to, first of all, go here, improve the quality of the observations, and then solve the problem of maximum observation entropy, since the quality of the observations are way better. And this type of behavior was not able to be reached by any other performance over observations only, because there was no way for the agent to actually perceive this difference, which was passed through the regularization. So this is, let's say, a landscape of what can be done in POMDPs once we accept to have to deal with observations only. POMDPs are a rather difficult problem, and most of the time the literature doesn't tackle POMDPs with observations only or Markovian policy over observations like we did here. The learning non-Markovian policies is rather hard. It requires a little knowledge about how to do stuff in practice. And for this reason, we wondered how to go beyond observations while keeping the formulation rather easy. So in the second paper, we addressed a different problem, not the intrinsic limits of the POMDPs for the task of pure exploration, but rather how to perform pure exploration once we assume to have access to a different kind of model, namely a model over the latent space. So this can be generally used both through exact models or approximate models, and we studied the so-called belief formulation. So in the belief POMDPs in general, the agent interacts with POMDPs as we have seen before, but while interacting, it learns a model of a distribution over the latent space so that it can sample states from such a distribution, which is called belief. So that the model is updated every step or every few steps. And in every step, the agent has some belief where it is with respect to the latent space S. And it samples the states from this distribution. So the problem setting is the same as before. We just added a further model, which we call belief model, which provides distribution over states. And a way to update this model, this might be an exact update like Bayesian updates, but it might be also approximated updates as done in the most recent literature. We focus on the exact update, and then we tested against approximated update as well. But again, what you will see now on is not about how you learn belief models or how you learn models over the latent space, but rather how you use them as soon as you have some model. The analysis is agnostic with respect to what kind of model you're using. And in such a model, more interestingly, the agent is able actually to perform decisions with respect to a more rich set of information, like, for example, the belief itself, or the so-called beliefs state, which are the states sampled from the model over the latent space, or trajectories over these. Interestingly, dealing with observation, with beliefs, and dealing with recurrent learning model, as it is usually done in order to learn such models, allows the agent to define Markovian policies which are implicitly no-Markovian, since they are conditioned over statistical quantities which were learned in a recurrent fashion. And that's what we have done in this second paper. So we presented another objective, which we called the maximum believed entropy. This is still a trajectory-based formulation. So we first interact with the environment and extract trajectories over beliefs. And then we use this trajectory over beliefs, so trajectories over latent models, to sample states from them. And then we try to optimize the entropy over the states we sampled from the model we learned through some conditional entropy again that you can see here. So dealing with such an objective has some positives, mainly the fact that the model we are using to sample objects from, like sample believed state, is a latent model. So the agent has pretty much control over it. And more interestingly, maybe, it's implicitly no Markovian, since it's usually learned through recurrency, so that simple Markovian policy over belief-based quantities are rather rich policies indeed. On the other hand, we described in our paper, and unfortunately I don't have enough time to go in details, but we described the problem of hallucinations in such a task, which is the following. The agent is supposed to visit the state as much uniformly as possible, but the state it has access to is the one sampled from the model it has already learned. In this way, the agent is actually able to exploit the learning problem in order to learn highly entropic representations over the latent space. And this is what we call hallucination, meaning that the agent will only objective will be to keep the latent model as much uniform as possible, so as that as soon as it samples states from it, the objective will be rather good because the entropy will be rather good. So this is an extremely important point to take into account, and that's what we focused on in this paper as well. So to go beyond this problem of hallucinations, in order to still use policy gradient methods, we defined a regularized version, which is pretty similar indeed to the regularized version you have seen before. We defined the entropy over the belief model, which is, since it's a joint distribution, is just the summation over the entropies. And we defined a lower bound towards of the original objective, which consisted of the expectation with respect to the believed model, to the believed states, regularized with respect to the entropy of the models you have encountered while interacting with the environment. So this regularization takes explicitly into account the fact that you are interacting with the environment, but some states that you are sampling for your model might be generated by some models that are extremely entropic, and you shouldn't trust them. So again, the rationale is rather similar to the one before, even if the problem is rather different. You want to encounter while interacting with your POMDP beliefs that are rather unimodal with respect to specific states, rather than beliefs that are really uncertain about which state you could be. And once we have noticed that, we performed some two examples. Here I presented some really simple case with a grid world, but with extremely bad quality observations. And as you can see here, we made the similar tests, but with different performances. In particular, we used a different policy, which was able to leverage the use of belief. So the performances might be slightly different with respect to the trends you've seen before. But again, we plotted the true state entropy using either the true state entropy itself for updating the policy, the observation entropy over the observation entropy as a feedback. And as you can see here, it performs pretty in a stable way, but yet pretty poorly. The believed entropy, so using this objective without any kind of regularization. And as you can see here, it performs really poorly. And the regularized version, which is able to recover at the very end. What happens here? Actually, if we look at the entropy of the beliefs, so the entropy of the latent model learned while interacting with the environment, we notice that in the maximum believed entropy over here, hallucinations take place. So the agent is learning almost random models over the latent space, and this leads to a really bad performance over the true latent states. On the other hand, the believed entropy does incur into some price dealing with beliefs, but it is able to recover since we are actually regularizing for this quantity. And as soon as it is able to take into account this quantity, it is able to increase the performance. And in general, we notice this kind of behavior in all the experiments. Yes, Samuel?
Could you maybe, I'm a bit confused between the difference between the, when you sample a belief, so B, the variable B, and then when you sample a state from B.
I see.
So B,
Yes.
B is like a latent vector, right? But how do you then sample from B?
So B is generally a distribution. We used beliefs. So we are talking about distributions over the latent space, which are computed through an update method. For example, Bayesian update. So the expectation taken with respect to the trajectories of beliefs just consists of you interact with the environment. At every step, you update your belief, and you use and then you get a trajectory over beliefs. So the trajectory is built of the first belief you had, which is usually random. The second belief you have, which is an updated belief taken with respect to the observation you have seen, and so on and so forth. So you have a sequence of models. And you use this sequence to sample the states.
Right. So then it would be a bit similar to in a variational autoencoder that you believe B will be like the mean and the variance outputted by the encoder, but then the state S are like the Z samples from the.
Exactly.
Okay.
Yes.
Gotcha.
So you both take into account the models that are actually generating the samples, and then you want to optimize for the samples you actually see.
And I guess you pick B, like the family of distributions that you can measure the entropy in the closed form. Like I guess you use like Gaussians or something that is easy to
in
measure
general,
entropy from.
There are many methods to perform updates in closed form. We used like the easiest way is just use Bayesian update in the over the belief space, but you can use any kind of update you want. As soon as you fix the prior, you can do whatever you want. We didn't want to fix a prior in general, so we went with distribution-free updates. But yes, it's really up to you, and that's what I meant with saying that this general pipeline is agnostic on the way you are actually dealing with these models. As soon as you have access to a model which outputs, which consists of distribution over states, and that you are able to sample states from, then the pipeline is the same. We fixed this specific pipeline because it wasn't the focus on this paper, because we didn't even know how it worked in general. But there are many ways also learning approximated beliefs, or not even using beliefs and other models like the one you cited, but still the pipeline is valid. The pipeline is you should learn a model, but take into account the fact that the objective you are trying to maximize will make the agent more likely to learn bad models. And if you don't take this into account, dealing with pure exploration in POMDPs might lead to just poor performances just because you are learning bad models. Not because you're not performing well, just because the objective hides the fact that you are learning that. Because in pure exploration, the states are really entangled with the objective, and that's what makes this problem harder than standard RL. You are not able to decouple the reward from what you're seeing, and that's also what makes it interesting.
All right. Okay, thanks.
No worries. So just to conclude, And I was really short, so we might see some proofs. In these two papers in general, we addressed the problem of pure explorations in POMDPs. We wondered how to cover latent states without having access to them, and what is the price of doing so. In the first paper, we derived the fact that generally one can look at observations only, as long as these observations have a convenient structure or are well behaved. And this might not always be the case. When this is not the case, in order to recover from this fact, some additional information about the observation matrix or about how these observations are emitted might be needed. Otherwise, the agent has little to do about it. And this is a common problem in POMDPs. In the other paper, we try to go over this limitation by learning a model so that the agent had access to it. And we address the problem of pure exploration in POMDPs. As soon as we have access to a latent model over a model over the latent space, sorry. And we proved that in general, this provides additional control since the agent is actually learning it and it knows exactly how it is behaving. On the other hand, we highlighted that in this setting, which is more likely to be scalable, probably, the designer needs to explicitly take into account the hallucinatory effect. Otherwise, the task might jeopardize the learning process as well. So we were interested into pure exploration because it's an interesting topic by itself. It allows to derive policies that are able to visit uniformly the state space, and some tasks like exploratory tasks might be requiring such policies. But on the other hand, pure explorative policies have been shown to be really good in general in the unsupervised RL framework, to be used as pre-training policies, so that as soon as a reward is provided to the agent, it is at least able to explore the state uniformly and focus just on the rewards that are important to it. On the other hand, it might be a starting point to perform data collection for offline RL. It does not provide coverage over the state actions, and next state as well. But adding regularization to these policies does induce more rich behaviors. And for this reason, it might be interesting to use these policies in for offline POMDPs. And finally, we noticed that taking into account these specific problems of hallucinatory effect leads implicitly to belief models. And in general, we expect to lead to good quality latent models, because we are restraining the models to be uniform. We are forcing the model to be good in the sense that it needs to extract one state with high probability. And this might be an interesting way to learn good representations in POMDPs as well. So while we didn't provide one fit-for-all solution in these papers, we think that together that might pave the way towards more interesting approaches in POMDPs. And here are the references. Feel free to have a look later on, and feel free to make questions. Thank you. Oh, I have proofs as well if you want, but I don't know, it depends. It was 50 minutes are rather long.
Yeah, I think it's better if we start with questions because we only have 10 minutes until the end of the hour.
Yes.
And then maybe there will be questions on the proof so that you can show the proofs.
Hope so.
So guys, please feel free to unmute yourself if you have a question.
Otherwise, it's gonna be proof.
Maybe I will start with one.
No
we can delay the proofs by a couple of minutes. Actually, it's a bit related to the maths though, because these objectives, a lot of them are in function of like a conditional entropy and an entropy, right? So
yes.
That's like a mutual information. You can probably re-express that as mutual information, right? Like, did you have like a thought of like how a lot of some of the bounds that exist maybe in like in information theory and machine learning on mutual information could like be applicable here. Is that something you guys explored a bit?
No, we didn't. But it's actually what we are trying to go for in the next phase of this work. We try to be as let's say lean as possible in the derivation, but mutual information in general is really interesting as an objective, and it's the same objective. You just need to add one term. So I expect that you would end up doing slightly the same thing with a little more nuance due to the additional terms you are adding. We are investigating the term that would be added if we go with mutual information in general, but they were not needed over here. They might needed in the multi-agent setting, but this is an ongoing problem.
But I think in maybe one of the later slides, when you have like a beta coefficient, it seemed that there was something about they look like isn't that like a bit of mutual information by any chance? It's conditional entropy minus entropy.
Yeah,
it's negative mutual information, I guess.
Yeah, it's not exactly the same. The terms are really similar, but they end up being different objects. So you cannot use bounds for that kind of bounds. But I think that using mutual information in general would provide some insights. It was not used in general for the pure exploration task, even for MDPs. And so it's an open topic, like how to leverage that kind of information approximation bounds, like that kind of super nice bounds, to have more rich description. And it seems like it might be needed to pass through mutual information as soon as you have more than one agent. Because then you need to, transfer information between the states that are seen from one agent and the other. And that's what we are currently trying to solve, to perform a pure exploration in multi-agent games. Because, the introduction was talking about me doing multi-agent stuff, but here there is no multi-agent stuff. So, the next step would be to deal with coordination in such a task, and it seems that mutual information is the way to go.
Awesome. Okay. Well, there's a few of us in the group that also work on mutual information, mostly also to single agent RL. So myself, Mary as well, has done some work like that involves some mutual information between some two quantities.
Yes.
So it's still very broad, right? But if you want to chat more, like we could have a discussion.
I would love to.
Okay, if no one is wanting to go for it, I'm going to ask a second question.
Oh, okay.
I would like to know if I find the concept quite interesting, the unsupervised concept when you talked about data collection, right? Because
yes,
there's been quite a lot of excitement for world models recently, and how you can use them to train RL agents. But there is not that much work, I think, on how do you collect the data to train the world model. And it seems to me like a framework like yours could be very helpful there, because this is this whole thing about like the making sure that the model is not getting optimized outside of being a useful model.
Yeah. So in general, I would say that it's a fairly broad topic that doesn't coincide with pure exploration. There are some works which deal with how to collect the best data set in general, and I can provide you with some references if you're curious. And because data sets in particular are, how to collect data really depends on the task you are caring about. like also depend on the algorithm that you're gonna use. At least theoretically, offline methods does have like different guarantees based on the concentrations you are able to guarantee, the coefficients you are able to get over there. So based on the algorithm, you might want to collect data in a different way, I guess. But that's true enough that at least pure explorative policies are able to collect data which uniform distribution over the states. Policy, in order to optimize a more rich class of policies, usually you could just add some regularization, like try to keep the distribution, the policy as much far away from the uniform, the deterministic one, for example. Or add some further regularization as soon as you want to optimize for to have good distribution in the datasets. That looks also to the next state. So it's really a rich visitation. You know, you're almost uniformly visiting any possible tuple of state, action, net state. This is the best case of exploration, but it's rather hard and it has not really been explored in the pure exploration task, but it was explored in other works, I would say. Also take into account that I think that this is a good starting point because also the solutions that exist are rather easy. But on the other hand, the optimal policy of the pure exploration task is often deterministic in many settings. It's not Markovian in general, but it's often deterministic. And this is actually the worst case to collect data sets. So I think that it's a good starting point, but you really need to take into account the downstream task you will need to do later on, because it might really, you know, jeopardize everything. Because in pure exploration, I mean, if you have enough experience, you end up, you know, just following a perfect path that covers all the states, and that's it. But then, you know, if once you have reached that policy, you don't see that many transitions, you don't see that many actions, you are fine with the objective, but the data is not that rich. So you need to take care about that fact, about the optimality, that you are really going towards the bad direction, actually, I think.
All right, so basically you're saying that like visiting all of the states might be not enough if the way you visit those states are using very few like transitions between states and actions.
Yeah, there are some cases in which it's enough, but it's as far as I know, it's not enough. It's way not enough for offline RL. I'm not super familiar, but there is this setting called Jumpstart RL, in which instead of using an offline dataset, you use an initialization policy to perform learning. And in each episode of experience, you use a standard RL policy like Epsilon Greedy just in the very end. And you start using this policy at the very beginning, just at the very end, and then you start using before and before and before, up to the point where you just use a standard RL policy. And they have good theoretical guarantees about these performances, and they generally seems to work pretty well. I think it's over here. It's this one. Jumpstart reinforcement learning, and purely explorative policies actually do satisfy the conditions for which you should use them. So they do satisfy the conditions for which you can use Jumpstart RL. So that's what I was saying, like they might be good to many kind of downstream tasks, but it really depends on what you're using them. And in general, it's a problem of unsupervised RL in general. Like there is this huge literature that just focus on what will be the downstream task later on, and based on what you want to use that unsupervised phase, everything changes.
Yeah, I think that's the issue with like any unsupervised setting, right? Like you still define a prior with your method or your environment. Like there is like a prior you're having, and
exactly,
is if like the downstream task is not consistent with that prior, it's just, I think it's underdefined, right? You can you could always find an adversarial example of a task that like would not work no matter what you do unsupervised.
Yes, in general, the prior here in all these works is set in either which function you want to optimize for, which could be, I don't know, some norms or something, or the entropy, and which models you are looking for. But these two are the real priors in these settings, and I don't know of general works on unsupervised RL, like trying to, generally learn a good model, word model in an unsupervised fashion. But I would say that it's really not my expertise, so I might need to look a little about it.
Fair enough. Fair enough. But yeah, thanks for the insights though. Like that's super interesting.
No worries. No worries at all.
Okay, so it's just 4, but I mean we can stay on if people have some questions, more questions. So maybe like let's wait maybe like a minute.
Yes. I will exploit this silence to ask you guys, in case you are in Edinburgh, and if you know someone which is gives a room away for some time, just let me know, because I noticed that the situation is really bad, flat-wise. So just know that I'm here, and I will be looking for flats in the next few months.
Yeah, we have like a mailing list. So like for the department. So did you get your Edinburgh email address yet, or are you going to have it much later?
No, I don't have one. I think I will never have one, because
okay,
I go, yeah.
Then I could send an email to the list and put you in CC and to see like if. But usually I love people like looking for rooms or advertising rooms on there. So you might get lucky with that.
Hopefully.
Yeah.
Sorry for the interruption, but okay.
Okay. Well, yeah. If there's no further questions, we'll I guess we'll wrap it up. Yeah. Thanks a lot for the presentation, Riccardo, and yeah, we're looking forward to see you in Edinburgh very soon.
Yes, thank you. I'm looking forward as well. See you soon.
See you. Cheers.
Bye.